Good afternoon. My name is Jonas Dor. My advisor is the Professor Jorge Munayar Neto, and as a co-author of this paper, Maximiliano Malik. I am from the São Paulo University, the Engineering School of São Carlos, and this paper is entitled Numerical Analysis of Steel Columns Considering the Walls on Fire Conditions. The main objective of this paper is to build a 3D numerical model of steel columns under fire condition, to know the behavior of the steel column on high temperature. The core of this paper is focused on the processing time efficiency, not really on the results. The results will be aborted on other papers. The analysis is divided in 4 steps. The first step is the thermal analysis to know the thermal field on the cross section. And the second step is an engine value analysis to find the buckling modes. We are interested on the first buckling mode. First buckling mode is the global geometrical imperfection. Considering the walls reaching the flange will be considered the imperfection positive and negative depending the way of the fire, direction of the fire. The third step is a room temperature analysis, like a displacement controlled experiment to find the maximum load, the buckling load, and the fourth step is a thermostructural analysis. Will be applied a constant load, a ratio of the buckling load found on the last step. The thermal models was studied 2 models. The first one is a single column considering the fire from all the sides. And the second model is with walls reaching the flanks and the fire action from one direction. The other side of the fire will be considered a heat loss. Thermostructural model was built using shell finite element for the column and 2 end plates on the extremities. The degree of freedoms on the bottom end plate, on a line above the web, a line of nodes on the end plate above the web, all the degree of freedoms is restricted except the rotation about the weak axis. And the top end plate, a line of nodes on the end plate, a line of nodes above the web, all the degree of freedoms are restricted except the rotation about the weak axis and the longitudinal displacement. The axial loads applied on only one node because this line of nodes is coupled and it has the same axial displacement. The 2 models, the first without walls and the second with walls reaching the flanks, considering the geometrical imperfection, positive and negative. The constitutive relationship for the steel is that recognized by the Eurocode 3. The thermal model was built using shell 131 finite element on the column and the solid 70 for the walls. The thermostructural model was built using shell 181 and solid 45 finite element. The thermal effect was applied using surf 152 finite element. Applying the thermal effect on this side, you can see the thermal field on the cross section is satisfactory and has interaction between the 2 different elements. To validate the thermal model was used results from another researchers, in this case Silva, Correa and Rodrigues, 2008. The results from that node point was performed an experimental test. The solid line is the results for the node pointed. And the other two curves is from a numerical analysis using supertemp calc, considering the two ways of heat loss preconized by the Eurocode 1. The analysis was did using ANSYS, and we can repeat these results satisfactorily. To validate the thermostructural model using shell elements was compared with another model using solid thin element from previous research. And the axial displacement for the single column has a good approach, and the lateral displacement has a satisfactory approach too. Was performed a mesh test to find the better mesh with good, satisfactory results and processing time, efficiency of the processing time. The first mesh, named Ref1, this red line, is the coarse mesh, but don't have satisfactory results. The more refinement mesh, named Ref3, has a good approach, but spend a lot of time. The second mesh has a satisfactory approach, but and we will be selected for the further works. Here we can see the pink line is a model using solid elements, is the reference line, and the mesh named Ref1, the blue curve, don't have satisfactory approach, and the other two has. The results, the axial displacement for the single column and the column with walls reaching the flange, you can see the critical time for 10% of buckling load ratio is about 20 minutes, and for the model with walls reaching the flange is about 60 minutes. The axial displacement for 20 minutes is about 3 centimeters, and for the model with walls reaching the flange is about half of the axial displacement. The lateral displacement of the single column is almost constant until the critical time. And for the model with walls reaching the flange is always increasing because the direction of the fire promotes a bowing of the column. This paper was focused on the efficiency of the computational model, and further works will include an axial restraint, emissivity, radiation emissivity 0.7, how Eurocode preconized, and heat loss. You can find more information in this website from my university, and you'll find in this link my master dissertation. I would like to acknowledge the Committee of Organization, the São Paulo University, the Engineering School of São Carlos, Structural Department, and the CAPS for the support of this research. Thank you.
Okay, Jonas, thank you. Questions? Questions?
Again? Yeah.
Could I just ask how your thermal analysis of the column embedded in the wall works? Does it actually take the radiation off the web back towards the embedded flange? Does it take any convection on the reverse side of the web, which I think would be quite an issue in reality?
Yeah. The heat loss of the other side of the fire, you say, heat loss?
No, I'm talking about the heat transmission from a web which gets very hot very quickly,
Yes.
via radiation in particular, towards the the reverse flange.
Yes, understand. No, was not considered. Only the thermal effect from one side and heat loss from another. There's no interaction by radiation between the parts of the cross-section.
I think in reality that
Yes,
would be
yes.
quite important.
But in the numerical model, it's difficult to do this.
Yeah, it is.
You didn't also consider the separation of the wall to the flange during the fire, because in reality you have a separation.
Yeah, the numerical model is difficult
after
to
a certain time.
because the thermal
We have
model
tested, as you
because
know.
the thermal model is one and the thermostructural model is another. Don't together.
We have carried out tests, as you know, in columns embedded on walls, and we saw this separation during
Because
the
of
fire
this,
test.
the experimental and the numerical
This will-
never is
Yes,
together.
this will change a lot the behavior of the column. If you consider completely attached, it's different to consider this gap. Any more questions?